Hi everyone, I'm Rahila Syed. I'm here to talk to you about a topic titled Journey of Developing a Performance Optimization Feature in Postgres. It is an exploration of how one can develop a feature which will improve performance of physical replication. This talk will be useful for developers who would like to contribute to Postgres or anyone who would like to learn more about physical replication. So let's get started with a journey of developing performance optimization feature. Let us look at the basics first. What is physical replication? Physical replication is a block by block or byte by byte transfer of WAL files from master server to the standby or replica. It transfers the entire database from one master to the replica. It does not transfer just selected tables or columns or rows of a few tables. It transfers the entire database. What are the different types of replication? Synchronous and asynchronous replication. This replication type is set using GUC parameter, which is named synchronous commit. There are various settings to this GUC parameter. One is off, which means it is asynchronous replication. The commit of a transaction on master does not depend on whether the change is sent to the standby or the wall records corresponding to the change is sent to the standby or not. Master commits its transaction and gives confirmation to the user without waiting for the transaction to be locally flushed to disk as well. So there can be a delay between sending a response to the user that the transaction has been committed and when the transaction actually is made durable. This can be done for performance reasons. The second setting of this GUC parameter, which is synchronous commit, is local. This setting means that the transaction is considered as committed and a user is notified of its commit only when the transaction has been flushed to disk. This is the mode which guarantees the durability of a transaction. The third mode is remote write, which means that a transaction is considered as committed on primary only if the transaction has been written to a file on standby, which is the WAL file. This does not mean that it has been flushed to disk as well, it just means that it has been written. The other mode, fourth mode, is remote flush, which you might guess that the transaction is considered commit to be committed on primary only when the transaction has been flushed to disk on standby. Remote apply means that the transaction on primary is committed only after the transaction or the wall corresponding to the transaction has been written to the files, flushed to disk, and also the changes have been applied to the database on standby. So, whatever you read on primary can be read instantly on standby. Let us move on to look at the flow of wall files in physical replication. There is a primary server where your data changes are made, like inserts, updates, or deletes. These changes are logged in the form of wall records. This results in wall to get inserted to first wall buffers, then they are written to disk, and finally they are sent they are flushed to disk and then they are sent to the standby. At standby, there is a wall receiver process which directly writes these wall records that are coming in from primary to wall files. It does not have any buffering there. After writing to wall files, these wall files are then flushed to disk. After getting flushed to disk, there is a starter process on the standby which reads these wall records from the wall files and applies them to the database. So, as you can see, from the time the data is written on the primary to the time the data is available on the standby, there is a bunch of round trips to disk that happens both on primary as well as standby. Now, let's look at what wall buffers are. As mentioned before, the changes made to the database are written or logged to the wall files. First, these wall records are written to wall buffers, and then they make their way to the wall files. So these wall buffers can be set by a GUC parameter. These are typically about 3% of shared buffers. Setting this value high is important if you have lot of concurrent workload, lot of backends connected to Postgres, writing and reading to tables, because all of these backends that are started on your Postgres database write to the same wall buffers. However, setting this value too high is also not recommended, because this will definitely hamper the memory consumption of your computer. Also, the wall files or the wall buffers are flushed periodically by wall writer process. So, for very small transactions, we make sure that the wall buffers are consistently flushed to disk, so the wall buffers can be reused by other backends. So this should not be set to very high value as well. Now let us look at wall fsync. Fsync is something when we flush the wall records to disk and they are made permanent and durable. For a synchronous commit, it happens during a commit on a primary by calling xlog flush. There is a process called a background writer, wall writer, which does the writing or the flushing of the wall records in the background. It tries to not hamper the progress of the transaction that's running on your database. It periodically tries to flush wall as and when wall buffer starts to grow. It tries to keep it in check, because if it becomes full, it will start slowing down the active transactions, because they will not have space in the wall buffers to write their own changes. Wall writer works on writing wall records to files, and periodically it also flushes them. Flush of wall files by wall writer depends on certain GUC parameters like wall writer delay and wall writer flush after. If the last flush happened less than wall writer delay ago, and less than wall writer flush after worth of data was produced, the data is only written to OS buffers and not physically flushed to disk. So now let's look at how to identify bottleneck in the wall sender process. This is the wall sender main loop, and let us see what are the operations that are happening in the wall sender main loop. Wall sender is a background process in Postgres which is used for sending wall records from primary to standby. It runs an infinite loop, and these are the operations that happen in that loop. As it starts, there are some housekeeping tasks that are happening. First, what you can see is a reset latch. Latches is used by wall sender to wait for the network socket to get ready. It sleeps on the latch till the network socket is ready, or till new wall records are available in the wall buffers to send. Then there are other checks for interrupts, because it's a long running process, it needs to be interruptible. There is another task where the configuration parameters are reloaded in the process, so that what's happen in a wall send handle config reload, followed by processing replies from the standby. Moving on, we can see a decision box, and that is the exit condition. The exit condition check in that loop checks if the standby is done receiving wall, which is indicated by copy done, as you can see on the screen, or if the output buffer is full. So when both the output buffer and the copy done are true, output buffer being full and copy done are true, the wall sender will exit. This is the regular or a clean shutdown of wall sender. Output buffer is something that is used by wall sender to copy wall records from wall buffers to the output buffer before sending the output buffer over the network. So if the exit condition is not met, which means either the output buffer is not empty, there are still wall records to be sent, or and copy done also has not been received, then it will go on to check if the output buffer is empty or not. If not, then it goes on to flush that output buffer to disk. Sorry, flush that output buffer to network. If the output buffer is empty, it will go on to read the wall into the output buffer. So this happens from either the wall buffers or the wall files. First, wall sender checks if the wall is present in buffers and reads from the wall buffers, otherwise it reads from the wall files. In case of large transactions, it happens that the wall sender has to go to disk because the transaction takes a long time to commit, and by the time the wall sender is ready to send this transaction, the wall buffer eviction logic has kicked in. So the wall records are no longer present in the wall buffer and the wall sender has to go to disk. This logic happens inside the read wall into output buffer block shown on the screen. So when the output buffer has been read, it is ready to be sent to the network as shown in the slide. If output buffer is not empty, it goes on to try to flush that output buffer over the network, like you see. So once that completes, it goes on to see if the wall sender has caught up or if the output buffer is full. That means there is a lot of wall in the output buffer to be sent to the network. So that is when the wall sender sleeps, because there is a lot of work to be done on the network front, and wall has to be sent over the network. So there is no point burning CPU cycles of the wall sender. So it sleeps till the output buffer is available to be written again, or it also sleeps until there is new wall record present in the wall buffers to be sent across the network. Now let us look at particular wall sender behaviors. One of them is that the wall sender currently sends wall records only up to the last known wall record that has been flushed to disk. This is done for a simple reason that we cannot have standbys get ahead of masters, because at the standbys we don't buffer anything. We just completely go ahead and write to wall files. So we need some gate check where we guard the wall files being sent to the standby, because we don't want to be written and made durable on standbys before they are flushed to disk on master. Also, for large transactions and which are long running, it happens that they accumulate in the wall because commit has not happened yet, and the flush of the transaction has also not happened, which results in them accumulating in the wall buffers. So going on inserting the wall records and generating more and more wall cannot send them over the network because the flush has not happened, and this results in the network being underutilized. When the transaction commits, you'll send all of these records in burst across the network. So that time the network will also get overwhelmed. This can also result in increase in the disk IO because since a large transaction can occupy space in buffers for a long time, chances of it being written out are higher, and thus it means that when wall sender is ready to send it, it will have to go to disk to read it. So let us look at perf profiling. This is used to profile the CPU consumption of a particular process. It samples the execution of various instructions on the CPU at a fixed interval so that when it is aggregated, you know where most of the CPU time is spent by the particular process. It also contains a call graph structure which records the full stack traces. So the commands that I've used for profiling are shown on the screen. Perf record generates perf.data, which is then used by a tool called flamegraph, which is used to visualize these call stacks and make it easier to understand. So let us look at the benchmark that I've run to profile the wall sender and the wall receiver. The slide shows the details of the benchmark. Um, and the configure flags used to compile Postgres is shown on the screen. We use O2 for compiler optimization, which results in improvement of the performance of Postgres cluster. Also, pgbench is used, which is a TPC-B like benchmark. Essentially, what I've tried in this benchmark is to have enough concurrent clients so that the wall buffers are used to their fullest, and the wall sender has to go on disk more frequently to be able to send wall records. So I have used somewhere from 16 to 32 concurrent clients. Hyphen J is the number of worker threads which is set to match the CPU cores. Hyphen F is the custom workload. This is what happens when the pgbench benchmark runs, or which transactions that are run. These transactions are user defined. It's a custom script which is generating large amount of wall. This is again used to fill up the wall buffers quickly. I have measured wall IO using pgstat IO. It is a monitoring function in Postgres which can give you disk input output numbers, and it is used for all the backends in Postgres. I have specifically used here for wall sender, measuring disk IO in wall sender. So this is the script that I have used. The main takeaway here is that I have run the benchmark at least 3 times, and between each run I'm making sure that the OS caches are cleared. Also, a custom script which is generates large amount of wall is used in the wall pgbench benchmark like mentioned. So let us look at a flame graph that shows the CPU utilization of a wall sender. Just to give a recap again, the benchmark used is actually on a setup which sets up synchronous replication between two VMs which are in different regions. One is in US, one is in India. This is done so that we can have high network latency. So the TPS is impacted by the amount of time the wall is taking over the network. So here what happens is that we can see the significant amount of time is spent over the network rather than waiting for wall to get sent to the standby. So if we optimize network consumption here, TPS is likely to improve. The time spent to send the wall is about 18.5%, and the time taken to receive it is 21.79%, which is shown by the send function call and the receive function calls respectively. In this particular case, we don't see a lot of overhead from reading from this because it was a 40 KB transaction that I ran with custom SQL and pgbench, and the wall buffers were around 8 MB. So the wall records didn't need to get evicted so fast. So whenever the wall sender wanted to send the wall records, they were available in the wall buffers. Let us look at another flame graph. In this case, I have used a large transaction. This transaction is actually the size of the wall buffer, which is 18 MB, 8 MB. So about 43.5% of the time is spent sending the wall to standby here, and about 17% of the time is spent reading the wall from disk. So here you can see libc underscore pread function come up, and that is because of large transaction. A lot of disk read is happening when such a large transaction is being sent by the wall sender. In this scenario, if you optimize disk read, we can improve the TPS. So let us look at the core idea of the performance optimization feature here. As you can see, when we send a wall after getting flushed to disk from master, it results in increase in the disk read and also inefficient consumption of network, especially for large transactions. So the idea here is to send unflushed wall from primary to standby and not wait for the wall to be flushed to disk on primary. This also modifies wall replication protocol to include flush pointer in the message, in the wall message that is being sent. This flush pointer is used by the standby to determine whether it is safe to write wall to disk or not. Wall receiver buffers the wall records until they are flushed on the primary. So until the flush pointer has advanced on the primary, the wall receiver has to buffer these records on its in its buffers. What are the benefits? So quickly, this will result in reduced application latency, especially when the wall reaches standby before it is flushed to disk on the primary. Wall data flows through the shared memory buffers rather than requiring disk round trips, so reduced disk I/O. There is reduced time difference between transaction flush on the primary and the standby since the wall records are continuously being sent. For large transactions, this means that most of the transactions wall records are already sent to the standby by the time the transaction is committed and wall is flushed on primary. So let us look at the wall sender changes as well. So specifically, what is done here is that the wall records that are being sent by the wall sender are divided into wall records that have been flushed and wall records that are unflushed. And wall that has not been flushed, which are after the flush position, are always read from buffers because they are not on disk, and wall before the flush position are actually sent from buffers, and if they are not present in buffers, the fallback is to go to disk. So wall buffers sorry the wall sender now reads more wall from wall buffers instead of from flush to disk wall files. Wall sender needs to be woken up as soon as enough wall is inserted and not wait for the record pointer advance when the flush has happened. So Instead of waking up the wall sender when the record pointer has advanced, we are waking up the wall sender after enough wall records have been inserted into the wall buffers. And that size of the wall records is currently 8 KB, because we can't send two small packets also, because that will result in more data being sent over the network, more time the network calls for sending the data are invoked. There are headers attached to each packet, so we can't send extremely small data also. So we wait for at least 8 KB of wall records to be written to wall buffers before notifying the wall sender. So let us quickly look at the benchmark results that I see. So I repeated the same benchmark that I mentioned before, with synchronous replication being set up between VM on primary and VM on which is standby in US. So what you can see here, that the custom transaction that I've used is around 40 KB, and the wall buffers is 4 MB, and also the network latency is high. And without the patch, the TPS is 125, and with the patch, with the changes of the wall sender to send unflushed wall, the TPS is slightly higher, which is 133, about 5% higher. The wall read IO has also reduced with the patch. So let's quickly look at the wall sender profile after applying the patch, which is to improve sending of wall records from sender. You see that in this, the send and the receive functions take up less CPU time now, because we are utilizing the network bandwidth more efficiently by sending smaller packets. You also see that the xlog send physical function has come up here, which means that now we are reading more from the buffers, and that function is getting invoked more because we are reading more frequently now, and smaller chunks of wall is being sent. This could result in net improvement, because the network is a bottleneck here, and if we reduce the time spent by CPU over the network functions, if we reduce that, we can see a gain in TPS. So now let us quickly look at the wall receiver changes. Since the wall receiver currently receives the wall records and does not buffer them, it writes these wall records directly to disk. We need a mechanism to hold off writing the wall records to disk until the flush has happened on the primary. The unflushed wall lives in standby buffers and not on disk. So with these changes, the unflushed wall will live on the standby buffers, and it can't be written directly to disk. And when the primary's flushed LSN will advance, the standby will then go ahead and write the wall records from buffer to disk. The writing to the wall buffers, reading from the wall buffers, and then writing to the disk file happens in the wall receiver. The wall buffer used is the same as the the infrastructure that is used on the sender side, and this is just adapted to work for the receiver context. There can be an alternative implementation at the receiver end as well, in which the writing to the wall buffers and reading from the wall buffers and writing to the file and eventually flushing it does not all happen in wall receiver, and it the wall buffers can be shared like how they are on primary. Wall receiver inserts incoming wall into wall buffers. This will eliminate the need of direct IO in wall receiver, whereas the IO will happen in a wall writer process, which will go on and read from these buffers, write and fsync the wall files asynchronously. This will also have one advantage of the startup process being able to read from buffers and fall back to reading from disk if they are not present in buffers, which currently does not happen. Currently, startup process reads from disk to apply the changes on standby. So this can also reduce disk IO in startup. So let us quickly look at the to do for this feature. As currently this feature is a work in progress feature. The vault sender changes are showing performance improvements, but vault receiver changes still need to be profiled. So there has to be a implementation and profiling on the vault receivers such that it does not impact the performance gain that we see on the vault sender side negatively. There is one to do here in the design of the vault receiver, which is that this approach relies on the fact that the wall buffers are big enough on the receiver to hold the unflushed wall from the primary. In case the unflushed wall that is coming from primary can't fit in the wall buffer size that has been allocated on the wall receiver, there will need to be solutions. Although this will be a rare scenario, but there will need to be some solutions to handle that. We can either write the records from the wall file from the wall buffers to a spill file when the flush pointer has not advanced on primary and wall buffers are full on standby. We can notify the sender to pause sending unflushed wall until the wall buffers here on the receiver are available, or we can have the sender's flush pointer information written in wall records and do not replay any wall until the LSN is greater than the flush pointer LSN. So these are the tasks that are to do in this feature. And this was a short introduction about the, the feature to improve performance of physical replication. I hope it helped you understand more about physical replication and how one can go about improving its performance. Thank you.